Okay, so let's continue here with our next section of the exams, which is going to be in the routing exam. And hopefully, as everybody knows, this is the new exam that is going to be replacing the BSCI. So you can see here from the CCNP webpage, if you go to cisco.com/go/CCNP, it will redirect you here. The difference in the exams is 642.901, which is BSCI, versus 642.902. Now, as you could tell, it says last data test is July 31st. And so that still gives us a couple months to go through those exams if you want to go through the older path. If you are going to take the BSCI exam, I would definitely recommend to look at the previous recording set that I did for BSCI, because as we'll see with the blueprints, when we compare the two, there are a bunch of topics that are no longer included in route that you will need to know in order to go through BSCI. So in either case, you could take BSCI or a route or a BCMSN or a switch. And likewise, ISCW and ONT are still available until the same upcoming dates. So from here, if you click on these individual exams, BSCI and route, it can eventually forward you to the Cisco Learning Network. And what you want to get to from here is the blueprint. So once you log in, click on View the Exam Topics. It's going to take you to the individual, the technical outline that corresponds to the exam. So here we have the previous iteration, the BSCI. It says things like implementing EIGRP, OSPF, ISDIS, routing features like redistribution, route filtering, basic services like DHCP, server client IP helper address, BGP, multicast, IPv6. Now for the new iteration in the routing exam, most of it is going to be fairly similar, where we have EIGRP, OSPF, BGP, IP version 6. The outline is a little bit more detailed here because now it says we want to plan the implementation. So we need to figure out what are the resources needed, like what type of platforms would we use, or what are the requirements of the actual physical routers, memory-wise, module-wise, that type of stuff. But technology-wise on the outline, there's a couple key points that are no longer there, mainly being IS to IS and multicast. So IS to IS typically is seen as more of a service provider-oriented interior gateway routing protocol. So this would go along with MPLS, which also has been removed from, I'm not sure if it was an ONT or ISCW before, but MPLS is no longer within the scope of CCNP as well. So ISDIS and MPLS kind of go hand in hand. So it does make sense that if they're removing one, they would also remove the other one. So we'll see the generic outline here is going to be fairly the same. EIGRP, OSPF, BGP, IPv6, then redistribution. So IPv4 or IPv6 redistribution. We'll look at both this week. We'll see they're fairly similar. If you understand one, you should implicitly understand the other. Then this last section, which is a bunch of stuff kind of thrown in there under implementing Layer 3 path control, which basically is talking about Layer 3 traffic engineering. Now, up to this point with switching, we looked at Layer 2 traffic engineering by changing the spanning tree root bridge election and by changing the spanning tree root port election. There's really not a lot that we can do from a path selection at Layer 2. We'll see when we get into the routing protocols here and look at the Layer 3 control. There's much more detail that we need to get involved with. So not only the individual IGPs, like changing EIGRP delay and bandwidth or OSPF cost, but also BGP and how its different attributes work. Change the BGP best path selection algorithm. We'll spend a bunch of time on that as a very important topic for BGP, understanding how it selects paths. Then also some miscellaneous features in routing like policy routing and static routing. We'll also look at how the enhanced object tracking and IPSLA agreement can also integrate with the routing features to add reliability to them. So that type of stuff is going to be covered in Layer 3 path control. Then we can see some minor stuff thrown in at the end, Describe broadband technologies. This would be things like PPP over Ethernet, possibly for DSL. Basic VPN technologies in GRE. I would assume here that they're not talking about IPsec, that they're just talking about basic layer 3 VPN. So we'll look at things like IP and IP tunnels and the generic routing encapsulation, the GRE tunnels, but that does not necessarily mean that we're talking about like an IPsec VPN or a Cisco VPN client. So any questions up to this point as to what is within the scope of the routing exam? Now, just like the switching test, as I recommended before, in addition to this class curriculum that we're going through, I would spend some time on the command line going through the examples that I am doing, because there will be the simulation questions in the exam. But also, it would be a good idea to look through the Cisco Press books that correspond to the routing exam. So either the official certification guide, the exam certification guide, or possibly like the quick reference. So you do want to know that marketing specific information that Cisco has in their exams. A lot of that is going to be part of what you would see for the possible planning phase of the implementation before we get to the actual configuration. So for our class here, we're going to be spending most of the time talking about the technology and then looking at examples on how to implement it. We will talk about the planning phase, so what is required to implement it before we get there, as we get to those topics. But definitely you want to take a look at least one of the Cisco Press resources before you actually sit for the routing exam. Okay, so any additional questions on anything we talked about in switching up to this point, or the general topic scope for routing? So in today's sessions here, we're going to spend a few minutes first talking about the routing process itself. How do we separate the internal routing process versus the switching process, and then the actual layer 2 packet rewrite, which is encapsulation, and then some other minor features in how routing works that it's easy to overlook this if you were being you were sticking very strictly to the blueprint. But we want to make sure that we understand the generics of routing logic before we apply them to a specific protocol. So once we get through this, our first dynamic protocol for the day will be EIGRP. So at a minimum, we'll get through all EIGRP, and we most likely should get in at least to the first portion of OSPF this afternoon. Now, up to this point, within the scope of switching, the only major operation that we looked at so far was the switch receiving layer 2 frames, layer 2 Ethernet frames in its physical ports, and based on the layer 2 CAM table, the MAC address table, the switch figures out, do I need to flood the frame as a broadcast, or do I already know where the destination is located, and should I switch it to that individual port? So with the layer 2 bridging, there's not a lot of intelligence that goes on into the to the forwarding, and there's also not a lot of operations that the switches actually perform with the frames. So switching, as I mentioned before, is also called transparent bridging, because the switches are not modifying any fields in the packet headers. Unless we get into things like the quality of service or possibly those additional security features we talked about yesterday, like the dynamic ARP inspection, IP source guard. Under normal switching parameters, layer 2 bridges are not going to change anything in the frame. Now, we also looked at a little bit that the inter-VLAN routing and how the layer 3 switching works. And the key distinction was that anytime a layer 3 device is introduced into the network, we are going to be changing the layer 2 header on a hop-by-hop basis. So from the routing point of view, when we receive a packet in our Fast Ethernet 0/0 interface, and we want to route it out a serial link that's running PPP, it means that we need to remove the layer 2 Ethernet header as the frame comes in. We need to replace it with a layer 2 PPP header that would go on to the serial link. So the router is going to do frame modification as the packets are moving between the interfaces. Now specifically, we can separate this into 3 different logical steps that are happening inside the router. We have the routing process, the switching process, and the encapsulation process. Now it's important to separate the 3 because there's different types of verification and different types of troubleshooting that we would go through if there's a problem in the routing process versus the encapsulation process. But technically, there are 3 separate operations that go on. Now, the first one, the routing process, this is typically what we think of when we're talking about the IP routing paradigm. This means that when a packet is received inbound, the first operation the router does is try to figure out what is the outgoing interface that we are going to forward the packet towards. And the way it does this is based on an operation known as longest match routing. So the router receives the layer 3 IP packet, or the layer 3 IP version 6 packet. We look at the destination layer 3 address. We look at what is the IPv4 or IPv6 address that the source is sending the packet to. Based on this, the ultimate goal of the routing process is to consult the routing table to figure out where does the packet need to go. What is the interface that it is going to leave out on? This is where our dynamic protocols or static routing are going to come in to populate the information in the routing table so the router can make its intelligent decision. So this is where OSPF or EIGRP or BGP is going to come in. This is going to help us find the outgoing interface. Okay, we'll also see that this is called the route recursion process. Route recursion, and we'll see this when we look at the command line, means that the router does one or more lookups, routing lookups, with the ultimate goal of finding the outgoing interface. So in certain circumstances, the router may need to do one routing lookup, or it may need to do 2 or 3 or 4. We'll see in the case of BGP, usually there's multiple routing lookups done before we can figure out what is the actual interface that we will forward the packet out. So once the router figures out what is the interface, now the routing process is done. The packet is now passed down to the switching process. Now this is not to be confused with layer 2 switching from an Ethernet point of view. This is what we consider the switching path of the router. Now the switching path will be defined by things like Ceph switching or process switching or fast switching. This is where we are moving packets between the interfaces, and this is also where load balancing will occur. So we'll see there is a distinction between how the packets are actually load balanced from a layer 2 switching point of view, not a layer 2 switching point of view, a switching path point of view, as opposed to the information in the routing table. So if the first step of the routing table says we should load balance, doesn't necessarily mean that we will. It's up to the switching path to determine if load balancing will actually occur. Then our third step, encapsulation, this is where we are actually building the new layer 2 frame. And this will be different depending on the individual encapsulation that we're using. So for Ethernet, this process would involve looking up the MAC address of the next layer 2 hop. For frame relay or ATM, it would be a lookup of what is the virtual circuit number. So for frame relay, that would be what is the DELC number. For ATM, that would be what is the VPI/VCI number. For point-to-point medias, like PPP links, packet over SONET, HDLC serial links, the logical process is a little bit simpler here in the third step, because when we send the packet on the link, there's only one other possible destination. It's the device on the other end of the point-to-point link. So we'll see here how the encapsulation process will be different depending on the individual media that we are working with. So back to the first step, the routing process. As I mentioned, we use a process that is known as longest match routing. Now what this means is that when the router looks at the destination IP address, there is a possibility that there are multiple routes in the routing table that could be used to reach that particular destination. So for example, if we have 3 routes in the routing table, and we are trying to get to the destination 1.2.3.4, if we have routes 1000/8 that goes out interface 1, 1200/16 that goes out interface 2, and 1230/24 that goes out interface 3, the router says technically all of these start with the number 1 in the first octet, so they all are valid routes for the final destination. So we need some way to distinguish between them. What the router is going to do is always choose the route that has the most bits in common with the destination. So here we see the third route, 1.2.3.0, has not only the first octet, but the second and third octet in common with the destination. So we're basically doing a binary AND, bit by bit, to figure out which route has the most bits in common with the final destination. Now, as we get into the Layer 3 path control and the Layer 3 traffic engineering, this feature is a very, very important point to understand in theory, because we can use this longest match routing feature in order to change the path to a particular destination or to different portions of the network. Especially when we get to features like aggregation or summarization, longest match routing feature becomes very, very important there. Now, once we have found the route to the destination, next step is that we need to find the outgoing interface. So here we've chosen the route as 1.2.3.0/24. Now, along with this route, there will be at least one of 2 attributes associated with it: a next hop value and possibly an outgoing interface. Depends on the individual protocol that we have learned the route from or how we have configured the static route. But normally, at a minimum, we would have a next hop value that tells us who is the neighbor on one of our connected links that we should use to reach that destination. Now, in certain cases, one route can point to a second route, where the second route points to a third, the third points to a fourth, and on and on and on. This is what we call the recursive routing lookup. Now, the ultimate goal of the recursive routing lookup is that it really doesn't matter how many times we have to keep looking it up over and over and over, as long as we end up pointing at a connected interface. Now, whether this be a physical connected interface like Fast Ethernet 0/0, or it could be a logical subinterface, or it could even be a logical tunnel interface. As long as it is some link that shows up as a connected route in the routing table, then we can pass the packet off to the switching process. So there's 2 possibilities for failure when we're dealing with the routing process. The first could be that we can't find the route to the destination, so we just don't have the route in the table. The second could be that there's some sort of recursive error that stops us from being able to figure out what is the interface that we should send the packet out. Now, the first error is a little bit more straightforward to see in operation. Usually this just means that you've configured your static routes wrong, or some network is not properly advertised into your dynamic routing domain. Second problem is a little bit more obscure. We'll see some issues with this when we get into VPN tunneling with the GRE tunnels or the IP and IP tunnels. Based on some misconfigurations that we can do, we can get the router into a recursive error where it cannot ever figure out what is the outgoing interface that we're supposed to send the packet towards. Now we get to the point in the routing process where what happens if we do a lookup in the routing table and we find the longest match, so it's the route that has the most bits in common with the destination, but we find that there are multiple longest matches. And these longest matches could either be coming from the same protocol, so for example, 2 OSPF routes, or they could be coming from different protocols. One is learned from RIP, one is learned from EIGRP. Now these two cases are going to be treated separately based on 2 different attributes of the route, called the metric and the administrative distance. The metric value, which is normally a hop count or some sort of bandwidth-based cost for the route, is going to be used to decide between 2 equal longest match routes within the same protocol. This means that if we are receiving 2 RIP routes inbound, and it's for the same longest match, RIP would choose the one that has the lowest hop count. For OSPF, it's going to be the lowest end-to-end cost value. For other protocols, we'll see it's going to be specific to their implementation. Now, if the equal longest matches, so for example, the destination 1, 2, 3, 4 we're trying to reach, and we have 2 equal routes that are 1.2.3.0/24, if they are from 2 different protocols, then we will look at the administrative distance. Administrative distance is basically going to be a tiebreaker between the different protocols. Okay, this is also sometimes described as the believability of the protocol. Basically, it's just a local preference. Figure out which routing protocol do you want to use first. And a lower value is better. The best value is 0 for a connected interface. This basically means that you cannot configure a static route or learn some dynamic route that would override an IP address that you have configured on your local link. So if I have the IP address 10.0.0.1/24 configured on my fast Ethernet, it means that I cannot learn through another protocol the route 10.0.0.0/24. My connected interface is always going to take precedence. So here we have the entire list. A lot of these in practice you're never really going to see. Like IGRP is deprecated, along with the EGP, the Exterior Gateway Protocol. ODR, on-demand routing, is a very obscure implementation. And then in our case, IS to IS is not going to be within the scope. But as we can see from the list, the most preferred protocol, dynamic protocol, would be external BGP. Okay, the EIGRP summary, that technically doesn't really count. We'll talk about that later this afternoon in EIGRP. But the most preferred dynamic protocol is external BGP. The reason why is that if you are learning a route from eBGP, it means that it is coming from a different autonomous system, and that destination is not located inside your network. So if we are routing BGP with our service provider to get to the internet, any routes that we learn from eBGP, external BGP, are not going to be part of our autonomous system. They're going to be part of someone else's AS. So this means that we should not use our internal gateway protocol, our IGPs like OSPF or EIGRP. We would not want to use those to get to the destination, because the IGP is going to take us back inside our own autonomous system somewhere. eBGP is going to take us out of our autonomous system into someone else's network. So beyond eBGP with a distance of 20, then the IGPs will be preferred in the order of EIGRP, OSPF, then IS to IS, and RIP. So RIP would be less preferred than an OSPF route. But again, this only is going to matter, the administrative distance, if the routes are equal longest matches. So for example, if we have a route that comes in 10.0.0.0/8, and this is learned from external BGP, and from OSPF we have the route 10.0.0.0/16, so the same prefix but 2 different prefix lengths or subnet masks, and we are trying to get to the destination 10.0.0.1, Even though OSPF has a larger administrative distance, this would be the preferred route, the OSPF route, because it is a longer match. So longer match routing is always preferred. The metric and administrative distance are only considered when there is a tie in the longest match. And again, the metric is when there's a tie within the same protocol. Administrative distance will be when there's a tie between two different protocols. So again, once the routing process is done, the router has now figured out what is the outgoing interface that I will use to get to this destination. Okay, that's the only main goal of the routing process. Figure out what is the outgoing link. Now we send the packet down to the switching process. Switching is where it is actually moved between interfaces. Now the specifics behind the switching paths are pretty much going to be outside of our scope. There's a lot of technical documentation on Cisco's website about how the Ceph algorithm works and why it is better than the other ones like process switching or fast switching. Pretty much nowadays, there's no reason that you would not be running Ceph in your production device. Okay, Ceph stands for Cisco Express Forwarding. Basically what it is an optimization of how the data is organized for finding out where the destination is reachable. Now the difference between the other ones, process switching versus fast switching. The first one, process switching, it means that every packet, you have to ask the general purpose CPU where it is supposed to go. So process switching is also known as interrupt switching. Basically it means that the routing process generates a CPU interrupt every time that you're trying to send the packet to a destination. Normally in production, if you do process switching, you'll see that you have very, very high CPU utilization, and you'll have very high utilization in the interrupt process. But we'll see when we get to the command line how you could troubleshoot this. But if you look at the show processes CPU or show proc CPU, and it says that the interrupt CPU percentage is really, really high, usually that has to do with some error in the switching path. That you should be doing Ceph switching, but you're falling back to process switching for some reason. Now the second one, fast switching, this is also what we call route caching. Route caching. Basically what this means is that we use that route once, switch many logic. Okay, this is also what used to be called multi-layer switching, where the first packet comes in to a particular destination. We need to do process switching to ask the CPU where it's supposed to go. Once we figure out where the packet's supposed to go, we now take that result and we put it into a routing cache. And now we can use the cached information for all subsequent lookups. So we're routing it once and then switching it many times. Okay, the problem with fast switching is that it is event-driven. It means that you have to wait until you have a packet going to the destination before you actually build the entry, before you start building the route cache. Whereas with the third option here, with Ceph switching, the route cache is pre-built before any traffic is actually forwarded. Now, Ceph is what runs in any of the hardware-accelerated platforms like 7200s or 7600s, and this information is replicated down to the line card itself, to the physical interface where the packet forwarding happens. Okay, this is like what we talked about previously in high availability for switching, how the higher level platforms can decouple the control plane versus the data plane. Because the control plane is the routing process. Okay, the routing process is where we're exchanging the routing updates with our adjacent neighbors, and we're building all this information to figure out where should the packets be going to. What are the outgoing interfaces? Then the information that goes down to the data plane for actual forwarding, this is what the Ceph table does. So the Ceph table behind the scenes is what we're really using to forward the packets. But in the hardware-accelerated platforms, the Ceph table is actually replicated down to the line card itself. So the line card really makes the decision about where the packets are going. It doesn't have to talk to the general purpose CPU and talk to the routing process. So this is why if the supervisor goes down or the route switch processor goes down, you can fall over to the second one with the stateful switchover feature and nonstop forwarding. And the line card itself is still able to forward because it has a copy of the Ceph table. So when we get onto the command line later, we'll look at how the Ceph table is built. Like I said, a lot of it is going to be outside of our scope. But we will take a look at some basic examples there. Okay, and as I mentioned here in the switching process, this is also where load balancing occurs. So for load balancing to actually happen, a couple of things need to be in agreement. First off, the routing process needs to say that we have multiple routes, but then the switching path needs to be actually configured to allow the load balancing. So just because you have multiple routes in the routing table doesn't necessarily mean load balancing will occur. And lastly, our third step, the encapsulation process. This is where we are doing our layer 2 packet rewrite. So this is where the router is building the new layer 2 header based on the media of the outgoing interface. So if the packet is going out an Ethernet link, it's going to build the layer 2 Ethernet header, and it will need to know what is the destination MAC address that is supposed to go inside of the frame. So this is where we will be referencing a layer 2 to layer 3 resolution table for Ethernet to figure out what is the MAC address that we're trying to go to. For frame relay, what is the data link connection identifier, or the DELC, that we're trying to go to. For ATM, what is the virtual path identifier and the virtual channel identifier, the VPI, VCI values. So in all three of these cases, we're basically trying to figure out, based on the layer 3 destination, so based on the IP destination, what is the layer 2 address that we need to put in the layer 2 frame. Now for point-to-point medias, like HDLC and PPP, so this would be something like a packet over SONET interface or a high-speed serial interface, a HISI interface. These type of links do not need layer 2 addresses, because if we have router 1 that is connected with a packet over SONET interface to router 2, when router 1 builds the frame to go out that link, there's only one possible destination, which is router 2, because physically it's a point-to-point link between the two neighbors. Now, multi-point interfaces like Ethernet, they need to do the layer 3 to layer 2 resolution process because there can be multiple destinations that can receive the frame. So in the case of Ethernet, it would be anyone who is in the same VLAN. In the case of frame relay, it could be any different virtual circuit in the service provider network. So based on the individual PVCs or permanent virtual circuits that you actually buy from the service provider. Now, the reason this last step is important, the encapsulation process, is based on our configuration, there can be some odd effects that we see from the routing process that actually have to do with the layer 2 encapsulation. A good example of this would be for static routing to a next hop versus an interface. Now, typically where you see this is on some sort of small design where the edge router uses just a default route to reach the internet. So let's say, for example, that we're running DSL as our access media, and we want just a default route to the internet. So we're not running any routing protocol with the ISP. Depending on how we configure the static route, either pointing to the next hop, to the interface, or to both of them at the same time, it can lead to some inefficiencies behind the scenes in the layer 2 encapsulation process. Now, in the first case where we are routing towards a next hop, we're saying here we have a static route to get to the destination 10.0.0.0/8. To get to 10.0.0.0/8, use the next hop value 1.2.3.4. Now, in this case, the router does not know what is the physical interface that the network 10.0.0.0/8 is located on. It only knows what is the next hop that we need to forward towards. What this means is that we now need to do an additional recursive lookup to figure out where is the destination 1.2.3.4. So it could point to another static route, could point to a dynamic route, could point to a connected route. In this type of case, when the layer 2 frame is built, we use the layer 2 address of the IP destination 1.2.3.4. So let's say, for example, that we have our Ethernet interface, Fast Ethernet 0/0, and it is the connected route 1230/24. The router is trying to figure out how to get to the destination 10.0.0.1. So the packet comes in, it says the destination address is 10.0.0.1. We now look in the routing table. In the routing table, we find the longest match. It is this static route, 10.0.0.0/8. It goes to the next hop 1, 2, 3, 4. Now we need to perform a second lookup. That's the recursive lookup. And we find that 1, 2, 3, 4 is reachable via 1.2.3.0/24 as connected. So the connected route is the longest match in this case. This now means that we need to figure out what is the MAC address that corresponds to the IP 1.2.3.4. So if we don't already know their MAC address, we would have to send an ARP request. If we do already know it, it's going to be inside of the ARP cache. Now, the other option here would simply be to point the destination out the interface. So we have the same type of logical route here, 10.0.0.0/8 via Fast Ethernet 0/0 versus the next hop. Now, the next hop we already talked about was on Fast Ethernet 0/0. So the end result is effectively the same route, that we're going out the same interface. The difference will be, who do we perform the layer 2 resolution for? In the case of the route going to the interface, we perform layer 2 resolution for the final destination. Now, what this means is that if we are going to the destination 10.0.0.1, 10.0, 10.0.0.2, and 10.0.0.3, we need to have 3 individual resolutions for the MAC addresses of these devices. So either we would have to ARP for them directly, or we would have to use some sort of workaround like proxy ARP on Ethernet. So we will come back to this later when we talk about policy routing and some advanced aspects of static routing. But this definitely is going to be a key point in basic IP routing logic that a lot of people skip over. It can have a very large negative impact on the actual operation of your router at the edge. So if you point a default route to the interface as opposed to the next hop, you can see that you'll have this gigantic ARP cache for basically every destination on the internet. Or worst case scenario, it's not going to work in that design because of problems with features like Ethernet proxy ARP. Okay, the other option would be the second bullet point, which is routing to a point-to-point interface. This is the case where it is valid to route directly to the link. If the link is point-to-point, like a point-to-point serial subinterface, point-to-point interfaces, since they do not need layer 2 addressing, we don't need to do any type of layer 3 to layer 2 resolution. We simply just send the frame out there. So if we have a PPP interface, we could point the route directly out there. The router's not going to need to do any type of layer 2 resolution. Okay, this question, what happens when the static route goes to the next hop and the interface? Now, when the first option pointing to the next hop, it means we do need to do a recursive lookup. So we need to do another lookup to figure out what is the outgoing interface. When we point to the interface, we do not need the recursive lookup because we already know the interface. So when you do both of them at the same time, you get the advantages of both features. So you skip the second lookup, you skip your recursive lookup, but also you do the layer 2 resolution for the next hop. This is actually the most efficient way to do the static route, because then you're skipping your second routing lookup and you know what layer 2 address you're trying to forward towards on that link. Because the next hop, it always should be some neighbor that is layer 2 adjacent to you. So in the case of Ethernet, it should be someone who is in your VLAN. In the case of frame relay, it should be someone who is on the other end of one of your virtual circuits. Okay, there's a question for the static route with the interface, you don't need to resolve the MAC address. No, you do need to resolve the MAC address, but you need to resolve it for the final destination. So let me draw out an example of this here. Let's say that we have router 1 that has 2 Ethernet interfaces. One of them is going to the inside network. One of them is the outside network. It's going out to the rest of the internet. Okay, the outside network is on Fast Ethernet 0.0. Inside is Fast Ethernet 0/1. Okay, so pretty straightforward design. Now, in a case like this, router 1 probably doesn't need any complex routing protocols. If this is the only edge router, we could just simply put a default route that's pointing out that direction. So we'll say something like IP route 0, 0, 0, 0, 0, 0, 0, 0. So 0 is the address, 0 is the mask, so it's everything. We'll say it's reachable out Fast Ethernet 0/0. Now what this means is that if router 1 receives a packet that is going to, let's say, the destination 10.0.0.1, it says the longest match for this is the default route. The default route recurses to the interface Fast Ethernet 0/0. But now when I am building my Ethernet frame, I don't know whose MAC address to use in the layer 2 destination address field. So what do I do here? Okay, router 1 basically does not know what its default gateway should be on that outside interface. So as a workaround, the router is going to send an ARP request for the final destination. It's going to ARP for 10.0.0.1. Now, unless 10.0.0.1 is actually physically on that outside segment, the destination is not going to reply back to the ARP. Because an ARP request is a broadcast, it's a layer 2 broadcast. Routers are not going to forward broadcasts between their interfaces. Now, what will work is that in certain cases, the router on the other end of the link will be running a feature known as proxy ARP. Proxy ARP basically means that if you receive an ARP request and it is for a destination that is not on the link that you received it in, so let's say this outside interface is the IP subnet 192.168.0.0. So router 2 receives this ARP request in, and it says it came in on the network 192.168, but it's going to some other destination 10. So they're not on the same subnet. Router 2 now looks in its routing table to see if it knows how to get towards the network 10. So if router 2 has a route to 10, it will reply back to router 1 with its own MAC address on the destination's behalf. So basically router 2 is proxying for someone else's MAC address. And most of the time, the iOS routers actually have this feature on by default. Now, it is a possible security risk. We'll talk about that later, why you normally don't want to run ProxyARP. But in most versions, it's on by default. Okay, so basically, router 1 puts an entry in the ARP table, or the ARP cache, that says the IP address 10.0.0.1 goes to the MAC address R2. The problem is now, for every destination that we are routing packets out onto the internet, we're going to have different addresses in the ARP cache that all point to router 2's MAC address. So for whatever addresses that the clients are going to, you're going to have an individual entry in the ARP cache. So if they reach 10,000 different addresses on the internet, then there's going to be 10,000 individual entries in the ARP cache. Because we're trying to resolve the final destination, and it just so happens that router 2 is trying to fix that with the Band-Aid solution, which is ProxyARP. Okay, but this is a case where you can basically run out of space in the ARP cache, or the ARP cache just gets so gigantically huge that it takes a long time to do the lookup. Because remember, this happens on a packet-by-packet basis. So every time a packet comes in, router 1 needs to figure out what's the destination layer 2 address. We'll look at this on the command line, and it will make a little bit more sense why you would not want to do this. Okay, so what's the solution? You need to route towards the next hop value. You should not route towards the to the interface. Okay, there's a question: what if the interface is assigned by DHCP, the IP address? There's actually a feature in the DHCP client of iOS that you can have it automatically install the route for you. So if router 1 gets its address through DHCP, router 2 most likely is going to advertise a default gateway to it. So router 2 tells router 1, this is your gateway address. The DHCP client automatically takes that next hop, and it inserts it as basically like a dynamic static route. So it's a static route, but it automatically was generated by the DHCP process itself. Okay, so it may seem a little trivial why we're even talking about this in the first place, but we'll see that when we get to BGP, understanding how the route recursion process works is very, very important. Because otherwise you could be learning a route from one neighbor and routing your traffic to a completely different neighbor and not really understand why the packet flow is as the final result. So your routing table may not 100% agree with what your actual forwarding is. Okay, any other questions up to this point with the general routing overview?